Overhead valve design. When Oldsmobile and Cadillac introduced their all-new overhead valve V8s in 1949, it wasn't the invention of a new technology. It was the moment an existing concept was perfected and unleashed on a massive scale. Overhead valve engines had existed since the early 1900s. Buick had used them in inline configuration since 1904, but the 1949 Rocket and Cadillac 331 were the first overhead valve V8s to be mass-produced in volume and offered in mainstream American cars. And that changed everything. Until then, most American engines were flatheads, simple, reliable, and easy to build, but held back by poor airflow and low thermal efficiency. Their intake and exhaust gases had to twist through awkward, restrictive paths around the side of the cylinder, limiting compression and strangling power. As post-war drivers demanded more speed and performance, flathead engines started to show their age. The new overhead valve V8s flipped that formula. By placing the valves directly above each cylinder and actuating them via pushrods from a camshaft inside the block, engineers dramatically improved airflow. These engines breathed cleaner, revved higher, and delivered more power per cubic inch. Combustion chambers could now be shaped for performance, wedge-shaped or even hemispherical, allowing for higher compression and better fuel burn. The result? More power, better fuel efficiency, and engines that ran smoother and cooler. Oldsmobile's Rocket 88 V8, a 303 cubic inch overhead valve engine making 135 horsepower, gave drivers performance that flatheads simply couldn't touch. Cadillac's 331 V8 was even more refined, producing 160 horsepower with exceptional smoothness. These weren't just better engines. They were a turning point. They marked the beginning of the modern American V8. At the same time, European automakers were taking a different path. Brands like Jaguar, Alfa Romeo, and Ferrari explored dual overhead camshaft (DOHC) designs, with camshafts mounted in the cylinder heads for precise valve control at high revolutions per minute. These engines were marvels of precision but came with trade-offs: complex timing gear, high machining costs, and delicate tolerances that didn't scale well to mass production. In contrast, the American overhead valve design was brilliantly simple. It delivered strong, low-end torque, was easy to service, and could be built by the thousands with consistent quality. That made it ideal for American roads, where big cars, long distances, and smooth cruising were the norm. Drivers didn't need 7,000 revolutions per minute redlines. They needed torque at 2,000, and overhead valve V8s delivered exactly that. By the mid-1950s, nearly every American automaker had adopted the overhead valve layout. It became the default architecture for everything from family, sedans, and pickup trucks to fire-breathing muscle cars. From the Chevrolet small block to the Chrysler Hemi to the Ford FE series, the pushrod V8 became the beating heart of Detroit's golden era. And it didn't end there. Decades later, the overhead valve V8 still lives on. General Motors' modern LS and LT engines, Chrysler's Hemi, and some Ford V8s still rely on the same cam and block architecture, now enhanced with electronic controls, advanced materials, and precision fuel delivery. The basic concept remains as effective as ever. While Europe's DOHC engines came to dominate in racing and luxury markets, American overhead valve engines won the real-world battle. Affordable, durable, powerful, and easy to maintain. They put serious horsepower within reach of the average driver and redefined what American performance looked and sounded like. The overhead valve V8 wasn't born in 1949, but that year, it grew up and took over the world. Small block V8. When Chevrolet unveiled its new small block V8 for the 1955 model year, it changed what an American engine could be. Engineer Ed Cole and his team built something light, compact, powerful, and easy to build. An engine that would define performance and practicality for the next half-century. Before 1955, most V8s were bulky and heavy, with long-stroke designs and deep skirt castings that prioritized durability over responsiveness. Cole's team started fresh. They used thin wall casting to save weight, standardized a 4.4-inch bore spacing, and engineered a short-stroke crankshaft that allowed higher engine speeds without sacrificing reliability. Stamped steel rocker arms, reduced valve train mass, and a simple pushrod layout made the motor easy to service. The result was a 265 cubic inch V8 that produced 162 horsepower in its mildest tune and up to 195 in optional form, numbers that gave Chevrolet an instant advantage. It wasn't just powerful, it was efficient to produce. The engine block, heads, and ancillary components were all designed for high-volume casting and machining, keeping costs low. In the process, Chevrolet created a motor that could fit everything from sedans to sports cars, boats, and later, pickup trucks. The architecture was so sound that it became the foundation for every Chevrolet small block that followed, from the 283 and 327 to the 350 and modern LS series. European manufacturers at the time were still constrained by taxation systems that penalized large-bore engines. Cars from Britain, France, and Germany often used narrow-bore, long-stroke designs that favored smoothness and efficiency at low speeds but limited airflow and peak power. Their complex multicam valve trains and hand-built castings produced beautiful engines, but at enormous cost. Chevrolet's oversquare design, larger bore, shorter stroke, allowed more valve area and better breathing, giving it far greater volumetric efficiency per cubic inch than European engines limited by bore taxes. In 1955, American assembly lines could turn out thousands of small blocks a day, each one nearly identical in balance and tolerance. In Europe, a high-performance engine from Jaguar or Ferrari was still assembled largely by hand. Chevrolet's innovation wasn't only mechanical, it was industrial. They proved that high performance could be mass-produced. The numbers tell the story. Over 108 million small block V8s have been built since 1955, powering everything from Corvettes and Camaros to Impalas and C10 pickups. Its power-to-weight ratio, affordability, and adaptability made it the most successful internal combustion design in history. European sports cars needed 6 or 12 cylinders to produce similar power. Chevrolet's Compact 8 did it with half the parts, lower cost, and unmatched durability. It embodied the core advantage of American engineering: simplicity refined by scale. 70 years later, the DNA of the 1955 small block still lives inside Chevrolet's LS and LT engines. The bore spacing, pushrod layout, and compact proportions remain largely the same. What began as Ed Cole's efficient little V8 became the most influential engine ever built. Proof that innovation and accessibility could coexist, and that Detroit could out-engineer Europe not with complexity, but with brilliant simplicity. Rochester Ramjet System. In 1957, Chevrolet did something no American manufacturer had done before. They brought mechanical fuel injection to the mass market. Their Rochester Ramjet system turned the already potent 283 cubic inch small block V8 into a legend, the first U.S. production engine to officially claim 1 horsepower per cubic inch, 283 horsepower, from 283 cubic inches. That figure came with the optional fuel injection package. Not every 283 made that much power. Only the top-tier version, equipped with the Rochester Ramjet, hit the magic number, but still, it was a milestone, especially for a showroom stock engine. Until then, almost every gasoline-powered car used a carburetor. Carburetors worked by drawing fuel into the airstream using the Venturi effect. They were cheap, easy to service, and generally effective but limited in precision. Changes in altitude, temperature, or throttle position could throw the mixture off. Tuning them was part science, part guesswork. Fuel injection promised something better, delivering fuel under pressure, with accuracy and consistency across the rev range. But for years, it had been the domain of aircraft, race cars, and a few high-end European machines, too complex and too costly for everyday driving. Then came the Ramjet. Developed under the guidance of GM engineer John Dolza, the Rochester Ramjet was a continuous flow mechanical fuel injection system. It used an engine-driven pump to deliver fuel under pressure to calibrated nozzles at each intake port. The system adjusted fuel delivery based on manifold pressure and engine speed, allowing more precise metering than any carburetor could manage. The result? Sharper throttle response, smoother cold starts, cleaner combustion, and better mid-range torque. Now, Chevrolet wasn't the first to put mechanical fuel injection in a road car. Mercedes-Benz beat them to it with the 300 SL Gullwing in 1954, using a Bosch system derived from aircraft designs. Alfa Romeo and BMW had also experimented with Kugelfischer mechanical injection in limited production and motorsport settings. But those were exotic, expensive, hand-built systems designed for boutique performance. Chevrolet's breakthrough was in scale. They built a system that could be mass-produced, installed on an assembly line, and sold to the average customer at a fraction of the European price. In 1957, you could walk into a Chevy dealership and order a fuel-injected Corvette or Bel Air right off the lot. The system wasn't flawless. The early Ramjet units were notoriously sensitive to wear and vacuum leaks. They required meticulous setup and didn't tolerate neglect. But when tuned properly, they worked, and worked well. The Ramjet-equipped 283 delivered smooth, muscular power and a level of drivability that carburetors simply couldn't match. That year, the fuel-injected Corvette became the fastest American production car, and Chevrolet gained serious engineering credibility. While European manufacturers pursued fuel injection to extract high revolutions per minute precision and top-end efficiency, Chevrolet focused on torque, usability, and affordability. That defined two divergent philosophies: the European path to racing purity versus the American pursuit of everyday muscle. By the early 1960s, mechanical systems began giving way to early electronic fuel injection, EFI, and the Rochester Ramjet was phased out, but its legacy was cemented. It had taken technology once reserved for aircraft and endurance racers and made it accessible to everyday drivers. The 1957 Ramjet wasn't just a cool option box. It was a statement. It proved that Detroit could innovate on the global stage. It set a performance benchmark and laid the groundwork for America's decades-long evolution in fuel injection. And it reminded the world that advanced engineering didn't have to be exclusive. It could be mass-produced, bolted onto a small block, and driven home from the dealership. That's how Chevrolet made history, 1 horsepower per cubic inch at a time. Cross-plane crankshaft design. The cross-plane crankshaft is the quiet powerhouse behind the unmistakable rhythm and torque of the American V8. Its geometry, refined in the United States during the 1920s, turned large engines into smooth, tractable machines and established the sound and feel that came to define American performance. A cross-plane crankshaft arranges the 4 crank throws at 90-degree intervals, forming a cross when viewed from the end. This configuration balances primary and secondary forces, allowing a V8 to run smoothly even at low rotational speeds. Each bank of 4 cylinders fires evenly every 90 degrees of rotation, so there is always a power stroke underway, giving the engine a broad, steady torque curve. European engineers pursued a different path. Their high-revving inline 6s and V12s often used flat-plane crankshafts with crank pins 180 degrees apart. The flat-plane layout allowed faster revving and simpler exhaust tuning, but introduced secondary vibrations that required precision balancing and lightweight components. It suited racing engines and smaller displacements that lived at high revolutions per minute, but it produced less torque and more vibration at the lower speeds typical of everyday driving. American automakers valued the opposite qualities. Cars were heavier, roads longer, and comfort mattered as much as outright speed. The cross-plane crank delivered effortless low-end power and a calm, refined idle. It also tolerated looser manufacturing tolerances than flat-plane designs, making it cheaper to produce in large quantities without sacrificing durability. Combined with the pushrod valve train of post-war V8s, the result was an engine layout that could power millions of vehicles, from sedans and trucks to muscle cars. The firing order of a cross-plane V8 creates uneven exhaust pulses within each bank, producing the deep, syncopated rumble that became an American signature. That sound wasn't an accident. It was a byproduct of engineering for torque and drivability rather than pure revs. The exhaust rhythm told you exactly what kind of engine was under the hood, one built for instant thrust, not delicate precision. By the 1950s, every major American manufacturer had embraced the cross-plane layout. Chevrolet, Ford, and Chrysler refined it with stronger materials and lighter rotating assemblies, but the basic geometry never changed. It was ideal for engines operating between 1,500 and 5,000 revolutions per minute, the range where most American cars spent their lives. European makers could point to smoother V12s or more responsive flat planes, but for sheer usability and production simplicity, the cross-plane remained unmatched. Even today, the design endures. Modern Chevrolet LS, Ford Coyote, and Chrysler Hemi engines still use cross-plane cranks because they provide the balance, longevity, and torque characteristics drivers expect from an American V8. A few specialty cars, notably the Ford Mustang GT350's flat-plane Voodoo V8, explored alternatives for racing-style performance, but those remain exceptions proving the rule. The cross-plane crankshaft exemplifies the American engineering approach, robust, practical, and optimized for real-world performance. It gave U.S. engines their characteristic feel, that steady, rolling surge of torque, and the deep mechanical rhythm that came to symbolize American power. Nearly a century later, the same design still anchors the heart of the American V8, a reminder that simplicity and balance can outlast even the most exotic alternatives. Stamped steel rocker arm. In 1955, Chevrolet introduced a small but transformative piece of hardware that helped its new small-block V8 out-rev and outperform engines, costing far more, the stamped steel rocker arm. It was a simple component, pressed from thin sheet metal rather than machined from heavy steel or cast iron. But it changed how efficiently valves could be actuated in mass-produced engines. Before this, most manufacturers, both in the United States and in Europe, used shaft-mounted rocker systems. Those setups were robust and precise, but carried heavy reciprocating mass and added mechanical friction. The extra weight limited safe engine speed, increased valve train wear, and required careful machining and alignment during assembly. For small-volume European makers such as Jaguar, Aston Martin, or Alfa Romeo, that complexity was acceptable because their engines were built in limited numbers. For a company like Chevrolet, producing hundreds of thousands of engines a year, it wasn't practical. The stamped steel rocker changed that equation. Using a ball and stud pivot, each rocker could move independently, with less friction and dramatically lower weight. The stamped shape provided excellent strength while eliminating the need for a solid rocker shaft. It also allowed precise valve motion at higher revolutions per minute, with less stress on pushrods and valve springs. The result was an engine that was lighter, cheaper to build, and freer revving than anything Detroit or Europe had ever produced at scale. From a manufacturing standpoint, it was a dream. Rockers could be stamped out by the thousands with uniform accuracy, heat-treated for strength, and installed without extensive fitting. Serviceability improved. 2. A single nut on each stud allowed quick adjustment, making routine maintenance faster and more consistent across dealerships nationwide. The design also tolerated oiling variations better than shaft mount systems, which relied on precise alignment for lubrication. European manufacturers continued with their heavier, more complex rocker assemblies well into the 1960s. The Jaguar XK engine, for example, used long valve stems and dual camshafts operating through intricate levers, beautiful in concept, but labor-intensive and expensive. In contrast, Chevrolet's stamped rockers delivered similar valve control using a fraction of the parts and cost. The lighter components reduced inertia, allowing the 265 and later 283 cubic inch small blocks to spin safely past 6,000 revolutions per minute, Impressive for an overhead valve pushrod design in the mid-1950s. The performance benefits were immediate. High-revving small blocks powered everything from Corvettes to Bel Airs and quickly became favorites in hot rodding circles. The simplicity of the valve train made it reliable under hard use, easy to service, and affordable to modify, traits that cemented the small block's reputation for durability and versatility. The impact of stamped steel rocker arms reached far beyond Chevrolet, Ford, Chrysler, and AMC adopted similar designs in the following years. And by the early 1960s, nearly every American pushrod engine used some variation of the ball and stud system. It became an industry standard that balanced cost, performance, and durability better than any alternative available at the time. Even in modern pushrod engines like the Chevrolet LS series, the same basic concept endures, updated with roller tips and improved materials, but fundamentally unchanged. The stamped steel rocker arm was a triumph of elegant simplicity, proof that thoughtful manufacturing innovation could deliver performance gains as significant as any change in displacement or compression. It gave American V8s the ability to rev harder, live longer, and be built by the millions, all for less money than the intricate European systems it quietly outclassed. Cast iron engine block construction. Few developments shaped the American auto industry more deeply than the industrialization of cast iron engine block production. Cast iron itself wasn't new. It had been used in engines since the dawn of motoring. In fact, Ford pioneered the use of mass-produced, one-piece cast iron blocks back in 1932 with the legendary flathead V8. But what truly transformed the industry after World War II was Detroit's ability to take that foundation and scale it with precision, consistency, and volume the world had never seen. Cast iron had the right traits for the job. It offered exceptional wear resistance, excellent vibration damping, and enough thermal mass to handle the heat loads of large displacement engines. It wasn't as light or as thermally conductive as aluminum, but it was tough, cheap, and incredibly stable under pressure, ideal for the powerful, torquey V8s that would define American cars in the decades ahead. By the late 1940s and early 1950s, foundries run by General Motors, Ford, Chrysler, and their suppliers had mastered high-volume green sand casting. Patterns and reusable core assemblies allowed them to form intricate internal coolant and oil passages with a single pour. These weren't boutique machines, they were engineered products cranked out by the thousands. Conveyor systems, automated pouring, and continuous mold lines meant blocks could be poured, cooled, machined, and ready for assembly at an astonishing pace. The result, a level of repeatability and output unmatched anywhere in the world. In contrast, many European manufacturers still operated on a smaller scale. Some high-end marques, like Rolls-Royce, Jaguar, and Ferrari, used aluminum for heads, or even entire blocks, chasing weight savings and refinement. These engines were often hand-finished, cast in low volume, and expensive to build. They were beautiful, but they weren't built for mass adoption. In America, cast iron let you build engines by the hundreds of thousands with rugged durability, and at a price that made high performance accessible to the average buyer. That toughness became the stuff of legend. A cast iron block could last hundreds of thousands of miles with minimal wear. It could handle high compression, tolerate abuse, and even survive aftermarket modifications like forced induction. During the muscle car era, these blocks underpinned engines, producing double or even triple the horsepower of earlier generations, all while costing a fraction of what an exotic European power plant might. The key was scale. Detroit didn't just make engines, they mass-produced them with scientific precision. A single plant could produce enough castings in a week to power everything from family sedans to full-size trucks to race-ready coupes. The same foundry techniques were used whether you were buying a base model Buick or a big block Chevelle. That kind of vertical integration and volume simply didn't exist in Europe, where smaller cars, smaller engines, and smaller factories were the norm. Even when aluminum engine blocks gained ground in the 1980s and beyond, spurred by emission standards and the push for fuel economy, cast iron never truly went away. To this day, it remains the backbone of heavy-duty trucks, commercial engines, and high-output V8s. Many modern engines still use cast-in-iron sleeves or compacted graphite iron blocks for added durability. It's not flashy, but it works. The mass production of cast iron blocks wasn't just a material decision, it was a manufacturing philosophy. It embodied everything American industry aimed for: strength through simplicity, affordability through scale, and performance without compromise. While Europe pursued engineering as an art, Detroit turned it into a science, and in doing so, it powered the most ambitious era of motoring the country had ever seen. Slipper piston design. The slipper piston may not sound revolutionary, but its arrival in the late 1930s completely changed how engineers packaged and balanced American engines. By trimming unnecessary mass from the piston skirt, designers made engines shorter, lighter, and capable of higher speeds without sacrificing reliability. The design became one of the key enablers of compact post-war V8s, especially the 1949 Cadillac and Oldsmobile engines that set the standard for modern automotive power plants. Traditional pistons of the 1920s and 1930s were long and heavy, with full skirts that extended deep into the crankcase to stabilize the piston as it moved. These worked well for long-stroke, low revolutions per minute engines, but as displacements grew and crankshaft counterweights became larger, the the pistons needed extra clearance to avoid interference. The result was tall engines with increased friction and reciprocating mass, not ideal for efficiency or high-speed operation. Enter Byron Ellis, an American engineer who developed the slipper piston concept. By cutting away portions of the skirt on either side, he created a lightweight piston that slipped between the crankshaft counterweights rather than riding outside them. The design allowed the engine's overall height to shrink, reduced reciprocating mass, and freed engineers to shorten the connecting rods and block deck height. The shorter stroke and lower mass also meant the engine could rev higher while producing less vibration. When Cadillac and Oldsmobile debuted their new V8s in 1949, the slipper piston was a crucial ingredient. It allowed both companies to build compact, over-square engines that were smaller and lighter than any previous flathead or long-stroke design. Cadillac's 330 1-cubic-inch V8, for example, produced 160 horsepower but weighed nearly 200 pounds less than its flathead predecessor. Oldsmobile's 303 Rocket V8 followed the same formula, creating the first family of true modern American V8s. Short, wide, and efficient. European manufacturers, still operating under bore-based taxation rules, rarely adopted slipper pistons in this era. British and French engines favored long-stroke geometries that maximized torque and minimized taxable bore size. Their conventional pistons required taller blocks and longer crank throws, adding weight and increasing internal friction. American engineers, unconstrained by such laws, could pursue over-square dimensions that emphasized high revolutions per minute, efficiency, and compact design. The slipper piston fit perfectly into that philosophy. Beyond packaging advantages, the design also improved durability and oil control. The reduced skirt area minimized side loading against the cylinder walls, cutting wear and improving efficiency. The lighter piston required less counterweighting, reducing crankshaft stress and vibration. These incremental gains added up to smoother engines that could maintain higher sustained speeds, an important trait as American highways and driving habits evolved after World War II. By the early 1950s, nearly every major U.S. automaker had adopted slipper-style pistons across their V8 and high-performance six-cylinder engines. The design became a cornerstone of Detroit's dominance in the muscle and luxury car markets, enabling engines that were compact, powerful, and affordable to produce. While Europe's long-stroke engines offered refinement at moderate speeds, American slipper piston engines provided unmatched power to weight ratios and compact packaging. That difference defined two automotive cultures, one focused on agility and efficiency, the other on raw, effortless performance. The slipper piston proved that sometimes, the smallest piece of metal in an engine can make the biggest difference. It helped shrink the size, weight, and cost of the American V8, and gave engineers the freedom to build the compact power plants that powered a generation of innovation. Hemispherical combustion chamber, or Hemi. In 1951, Chrysler introduced an engine that would become one of the most iconic names in American performance history, the Hemi. The hemispherical combustion chamber wasn't new. European automakers and aircraft engineers had been experimenting with the concept for decades. But Chrysler was the first to mass-produce it in a pushrod V8 configuration, making hemispherical combustion practical, reliable, and accessible to American drivers. A hemispherical combustion chamber is exactly what it sounds like, a half-sphere dome atop the cylinder. That dome shape allows for a smaller surface area relative to its volume, reducing heat loss and promoting a more complete burn. It places the spark plug near the center for even flame travel, and accommodates two large, widely spaced valves. One intake, one exhaust, positioned on opposite sides of the chamber. That cross-flow layout improves airflow, making for better breathing, higher compression ratios, and more power. Chrysler's first-generation Hemi, known as the Firepower V8, debuted in 1951. It displaced 331 cubic inches and produced 180 horsepower in its first year, which was exceptional for a passenger car engine at the time. The Firepower was overbuilt, with thick iron heads and a complex valve train, including dual rocker shafts per head, to manage the widely spaced valves. But the payoff was smooth operation, impressive durability, and a power-to-displacement ratio that rivaled more exotic engines. European automakers like Alfa Romeo, Peugeot, and Mercedes-Benz had used hemispherical or semi-hemispherical chambers since the 1910s, particularly in racing. Many of these engines featured dual overhead cams for precision valve timing at high revolutions per minute. But while those engines offered high revving performance, they were expensive to build, hard to service, and suited only to limited production sports or luxury cars. Chrysler's genius was in packaging hemispherical combustion into a robust, single-cam pushrod architecture. Using a cam and block design with rocker arms and cross shafts, they replicated the airflow benefits of European DOHC Hemis without the cost and complexity. That meant the Hemi could go into high-end Imperials and Chryslers, but also eventually into trucks, wagons, and even fleet vehicles. And the performance potential? Tremendous. Chrysler continued refining the Hemi through the 1950s and into racing. But it was the second-generation Hemi, introduced in 1964, that cemented the legend. The 426 Hemi was designed specifically for NASCAR and NHRA drag racing. With massive ports, heavy-duty construction, and race-bred heads, the 426 was officially underrated at 425 horsepower but capable of far more in competition trim. Nicknamed the Elephant for its size and power, the 426 became a fixture in Dodge and Plymouth muscle cars and a terror at the track. The Hemi's lineage is unmistakable. From the 1951 firepower to the race-winning 426, Chrysler kept pushing the limits of hemispherical combustion, while the rest of the world stayed cautious. European automakers continued to build high-efficiency heads, but rarely with the brute torque or bulletproof reliability of Chrysler's V8s. They stayed in limited production. Chrysler put the Hemi on the street. Even today, the Hemi name lives on. Chrysler revived the design in 2003 with the Gen 3 Hemi, offering modern tech like variable cam timing and multi-displacement systems, while still using hemispherically inspired chambers. True, the latest versions use flatter chambers and tighter emissions controls. But the core airflow philosophy, the big valves, the crossflow design, the central spark, is still rooted in that 1951 breakthrough. The Chrysler Hemi didn't just make more power. It redefined what American V8s could be: bold, smart, and engineered to dominate. It was the moment Detroit showed it could turn a high-concept European idea into a mass-produced performance icon. The Hemi made combustion chamber geometry cool, and it's still doing it more than 70 years later. Hydra-Matic. In 1940, Oldsmobile introduced one of the most transformative technologies in automotive history, the Hydra-Matic, the world's first mass-produced fully automatic transmission. It marked the point where American cars became not just faster or stronger, but easier to drive than anything else on the road. Before the Hydra-Matic, nearly all cars relied on manual gearboxes operated by clutch pedals and shift levers. Driving demanded coordination and mechanical understanding, especially in traffic or on hills. Engineers had experimented with semi-automatics, freewheeling systems, and fluid couplings, but none provided a seamless, self-shifting experience that was reliable enough for mass production. Oldsmobile's Hydra-Matic changed that overnight. The transmission used 4 forward speeds, a hydraulic coupling instead of a friction clutch, and a fully automatic hydraulic control system that shifted gears based on throttle position and vehicle speed. It was not only a mechanical breakthrough but an engineering masterclass in coordination, using pumps, valves, and planetary gear sets to select gears without driver input. Drivers simply selected drive, pressed the accelerator, and the car handled everything else. The system was developed under General Motors engineer Earl Thompson, who had previously worked on the Synchromesh manual transmission. His goal was to eliminate clutch work altogether, providing a smoother and more convenient driving experience. When the Hydra-Matic appeared in 1940 Oldsmobiles, it became an immediate success. Buyers loved its smoothness and ease, especially in an era when stop-and-go traffic was becoming more common. European manufacturers took notice but couldn't match it. Their market still favored small, lightweight cars with low-displacement engines that didn't generate enough torque to mask the inefficiencies of early automatics. In Europe, automatic transmissions remained rare well into the 1950s and 1960s, often limited to luxury cars like Rolls-Royce or Mercedes-Benz that used costly, low-volume hydraulic systems. Manual transmissions persisted because they were cheaper and more suited to high fuel prices and smaller engines. In the United States, the Hydra-Matic fit perfectly with the American driving experience. Wide roads, long distances, and big engines made smooth, automatic shifting a natural advantage. The transmission was strong enough for heavy cars, reliable enough for daily use, and simple enough for mechanics to service. By the late 1940s, Cadillac, Pontiac, and even some military vehicles were using Hydra-Matic units. During World War II, the U.S. Army used them in tanks and trucks, proving their durability under the harshest conditions. Technically, the Hydra-Matic was a marvel. The planetary gear sets allowed torque multiplication and gear ratio changes without direct mechanical linkage. The hydraulic coupling provided smooth engagement, eliminating clutch chatter and stalling. Maintenance was straightforward compared to European preselectors or complex manual synchromesh systems. More importantly, it changed how people thought about driving. For the first time, the car adjusted to the driver, not the other way around. It made motoring accessible to more people and paved the way for comfort-focused luxury cars that would dominate the 1950s. Within 2 decades, nearly every American manufacturer had its own automatic transmission, Powerglide, Dynaflow, TorqueFlite, all tracing their lineage back to Oldsmobile's Hydra-Matic. European automakers eventually caught up, but the culture had already diverged. In America, convenience and ease of use defined progress. In Europe, control and mechanical precision remained priorities. That philosophical split was born with the Hydra-Matic, a device that symbolized American ingenuity and mass-market innovation. It didn't just shift gears. It shifted the entire industry. Short stroke, high-bore design. After World War II, American engineers embraced a fundamental change in engine geometry that redefined performance and practicality: the short stroke, high-bore design. It was more than a mechanical preference. It was a statement of philosophy. While Europe continued to build small, high-revving engines limited by taxation and displacement laws, American manufacturers pursued large, freely breathing power plants that emphasized torque, smoothness, and reliability. Before the war, Most engines worldwide followed long-stroke, undersquare layouts, where the piston stroke exceeded the cylinder bore. This design produced good low-speed torque but limited revolutions per minute and airflow, since smaller bores couldn't accommodate large valves. European countries reinforced this pattern through taxation systems that penalized large bores, effectively discouraging oversquare engines. The result was smaller, high-speed engines tuned for efficiency rather than brute strength. American engineers faced no such restrictions. With vast highways, cheap fuel, and consumer demand for effortless power, they began favoring oversquare designs, larger bores, and shorter strokes. The benefits were immediate and measurable. The shorter stroke reduced mean piston speed, allowing engines to rev higher safely, while the wider bore provided room for larger valves, improving airflow and combustion efficiency. The combination delivered high power at moderate revolutions per minute and abundant torque from idle to mid-range. The post-war engines from Cadillac, Oldsmobile, and Chrysler showcased this thinking. The 1949 Cadillac 331 V8, for example, featured a 3.812 5-inch bore and a 3.625 5-inch stroke, distinctly oversquare for its time. It revved freely, stayed cool, and produced more horsepower per cubic inch than most European engines could manage even at higher revolutions per minute. By the mid-1950s, nearly all American V8s had adopted this approach, from Chevrolet's 265 and 283 small blocks to Ford's Y-block and Chrysler's firepower Hemi. This design philosophy fit the American driving environment perfectly. On wide-open highways, smooth torque and sustained cruising power mattered more than peak revolutions per minute performance. Oversquare engines could deliver high-speed comfort without constant downshifting, providing quiet, effortless acceleration for large sedans and convertibles. In Europe, by contrast, smaller roads, tighter corners, and high fuel costs encouraged the continued use of small-displacement, long-stroke engines that thrived on precision and revs rather than displacement. The short-stroke, high-bore configuration also worked seamlessly with the cross-plane crankshaft and pushrod valve train typical of American V8s. The lower piston speeds reduced stress on connecting rods and bearings, allowing larger engines to maintain reliability even when producing immense torque. It also simplified cooling and lubrication, critical for engines operating in a wide range of climates. By the 1960s, this engineering approach reached its zenith in the muscle car era. Engines like Chevrolet's 327, Ford's 427, and Chrysler's 440 embodied the oversquare ideal. They produced vast power bands that started just above idle and stretched through the mid-range, perfect for real-world acceleration rather than racetrack finesse. European engines with smaller displacements often needed to spin above 6,000 revolutions per minute to achieve similar power, while American V8s could deliver it at half that speed. Critics sometimes dismiss this philosophy as crude or inefficient, but its success spoke for itself. American engines were easier to build, maintain, and scale up in size. They were optimized for everyday usability and affordability rather than specialized performance. The combination of short-stroke, wide-bore, and pushrod simplicity gave American manufacturers the most flexible and reliable power plants of the 20th century. Even today, the legacy remains visible. Modern LS, Hemi, and Coyote engines still follow the same geometric logic: short strokes, large bores, and generous breathing area. The post-war American engineers weren't just chasing power, they were redefining what a road engine could be. The short-stroke revolution turned American cars into effortless cruisers and set the blueprint for an era where bigger really did mean better.